Yeah, today we're going to cover section 8.1. And really, 8.1 is about confidence intervals for population mean. It's when we know the population mean and the population standard deviation. Okay. So when we know the population mean and we know the population standard deviation, then we can do the techniques in 8.1. Okay. In the very beginning of your book, that section talks about that on page 358. No, like 8.2, 3, 4, as we go along, this stuff will change. We might not know the population mean. We might not know the population standard deviation, but there's other ways to develop confidence intervals if we don't know those things, or we do know those, like certain aspects of it. So I know that sounds goofy. It'll make more sense when we get there. But the first thing your book goes over is point estimate. Point estimate. And it says is a single number that is used to estimate the value of an unknown parameter. So, a point estimate for us is going to be like X bar, the sample mean, is a great example of a point estimate because it is a single value that is estimating the population mean, which we don't know, right? So single value estimating the population mean. Oh, wait, how much for population mean? Hold on a second. The population mean when the population standard deviation is known. I said that wrong. Sorry, so we've got to define what a point estimate is. It's X. We're going to consider it X bar. It just estimates the population mean. And then your book goes over margin of error. I'm not sure if it gives it a definition, a margin of error, but it's when we give, plus or minus a number to capture the error that's given. So your book says, plus or minus a number is called the margin of error. We need to determine the how large the margin of error so that the interval is likely contain the population mean. And I'm going to go over this once we get to an example. It's really easier to explain margin of error once we get to the example. But realize we're going to take our point estimate X bar. We're going to add some numbers above and below, and it's going to give us an interval. Now, that gap above and below the X bar, that's considered your margin of error, okay? Like, let's just look at an example here. Let's say we found out that an average, we take a sample and the average test score is 85. And it turns out for a 95% confidence interval, the margin of error is, let's say 5. Now, we're going to find all this soon, but I want to go over what this means now, okay? So what that means is the margin of error is what's added or subtracted from X bar. So that means our 95% confidence interval is 80 to 90, right? Because we're adding 5 to 85 and we're subtracting 5 to 85 because 5 is the margin of error. And now that doesn't mean that that doesn't mean 95% of the tests are between 80 and 90. That is not what that means at all. Okay? What this means is we're 95% confident the mean, the actual population mean, is between 80 and 90. Okay, that's what that means. We're 95% confident that the actual mean that we don't know. That's why I had to erase this up here because we don't know the population mean. Okay, we're 95% confident that the population mean is between 80 and 90. That's what this tells us. Now we're going to go into how to find the margin of error, how to find different confidence intervals and stuff like that. But this is what's going on. We're going to have an X bar because we know how to take samples, right? And then we're going to find the margin of error. we're going to add or subtract it from X bar. That gives us a confidence interval, right? And what the confidence interval tells us is whatever confidence we choose, so 95% confident, that the mean is between those two numbers. So it's not that 95% of tests are between 80 and 90. A lot of students think that's what that means, but it's not. It's that we're 95% confident that the mean is between 80 and 90. And that's going to be on the test, okay? Explaining this, interpreting the confidence interval is going to be on the test, where I give you something like this. We find that 95% confident for a sample is between, whatever is between 80 and 90. What does that mean? Oh, that means we're 95% confident that the population mean is between 80 and 90. Okay? 95% confident the population mean, not that 95% of the data is between there. That's not how that works. Okay? Okay, great. So let's get into the nuts and bolts here. How do you find these confidence intervals? Okay, and your book starts with an example, and I'm going to go with it. It talks about fourth graders. It says it starts on the bottom of page 358. It says, how can we measure the reading ability of elementary school students in a certain school district? Administrators are trying out a new experimental approach to teach reading to fourth graders. Simple random sample of 400. So n equals, I'm not 400, but 100. N equals 100. So 100 fourth graders is selected to take part in the program. At the end of the program, the students are given a standardized reading test. On the basis of past results, it is known that the scores of the test have a population standard deviation. So we know the population standard deviation is 15. The sample mean score from the 100 students winds up being 67.30. Okay? Now, again, and it goes back into, this is our point estimate. We want to know, we're really trying to find an interval for the population mean. We don't know what the actual reading score is for these students, right? We don't know the actual average for the population of students that take this experimental reading program. And we want to estimate what the actual average is. The actual population averages. We can do that with these techniques, okay? We can do that with these techniques. Now, what's nice is we've got 100 students, so that means we can use the central limit theorem, right? And remember, the central limit theorem we could use because this is over 30, it's 100. And with the central limit theorem, we could find the standard error. So the standard error, which remember was symbolized with this. It was really the standard deviation of the samples. And it was just the population standard deviation over the square root of n. That was from, I think, last section, right? The last few sections. So this winds up being 15 divided by the square root of 100. Oh, this math is easy. 15 divided by 10, that's 1.5. Okay? That's my standard error. So a standard error for this example is going to be 1.5. Now, that's not my margin of error. That's going to be found a little differently. That's my standard error. Okay? So it said, and I'm kind of following along as we go. It says, we will now construct a 95% confidence interval. Now, it's important that you state what level of confidence you want. 95% confidence level. Now, what this means is our alpha level is 0.05. These are kind of a vice versa statement. If you see alpha level of 0.05, all it means is that your confidence level is 95%. Okay? So if we wanted like 99%, our confidence level would be, or our alpha level would be 0.01. Okay, we'll get to one like that here in a minute. But I'm going to bring in this alpha level stuff. So alpha, that's the Greek letter for alpha. So alpha equals 0.05 means that we have 95% confidence. Okay, means we have 95% confidence. Okay. Now we begin with the normal curve because, of course, we have we can use the normal curve because of the high level of n, and then we need the z-scores for 95% confidence. So if you go back to our z distribution, right, our normal zero distribution here, And if we want a 95% confidence, what that means is if we've got these scores here where there's 95% of our data is in between, and we've got what? 2.5% on the outside. Okay. Now, you can find this in the calculator. This was that whole inverse norm thing. Remember in the calculator? Let's see if we can. I don't think your book does this even. I'm going to do it just to show you. We go over here and we click. What was it? I think it was vars.
Yeah. Second vars.
Yep. And then inverse norm.
Yeah.
Right? Now look, we want the z because we're wanting the z values. So we want these two z values, but remember, this was, for me, it was the area to the left of that value, right? Now, that means I've got to add up. If I want this one right here, I've got to add these two values together. So the area to the left would be 0.975 for me, right? Because it's 95% plus 2.5%. And then it's still 0 and 1 because this is the normal distribution. We want the z values. And notice we're going to round it to 2 decimal places. So 1.96. So the z value is 1.96.
Okay, what was that? 0 or 0.975, 0 and 1. Okay.
Yeah, it's 0 and 1 because it's the standard normal. Now look, I'll tell you, you can find this other one as well, which we need to. But what's nice is its symmetry. It should be negative 1.96, but we'll show that it is. So if I do second inverse normal, the area to the left of is 2.5, so 0.025. And we'll say it's the same thing, negative 1.96. Okay? Negative 1.9. So if we look at our z values, between negative 1.96 and 1.96 is 95% of our data. And we're using 95% confidence. So that's the z values that we need. Okay? That's the z values that we need. Your book just states that. I just wanted to show you where it was coming from. Okay? I wanted to show you where it's coming from. It's on page 359. It talks about critical value. So we're going to label that as our critical value because your book does. Actually, yeah, that's our critical value, 1.96. Now, you don't have to worry about the minus because we're going to actually do addition and subtraction. Remember, that margin of error includes addition and subtraction. So we do the plus or minus because of that. And we'll get to the math here in a second. Okay, so how do you find the margin of error? So the margin of error is equal to just your critical value times your standard error. It's critical value times standard error. I'm running out of room here. Critical value. Now our critical value is here, and our standard error is there, right? So for us, it's going to be 1.96 times 1.5 for this example. 1.96 times 1.5.
Okay, you wrote critical value. What is that? X dot SE? No, over in the box there.
Times. It's times. I ran out of room. Critical value times standard error. So when you multiply these together, the 1.96 times 1.5, you get 2.94. Okay, that's, for this example, that's our margin of error. Okay, that's what we're going to add or subtract to our x bar to give us our confidence interval. Okay, so I'm going to take x bar and then add or subtract my margin of error. And that gives us our confidence interval. So our x bar for this example is 67.30. And I'm going to add or subtract 2.94. Add and subtract, I should say, 2.94. So I'm going to subtract it first because we write the smaller number first. So 67.30 30 minus 2.94. That gives me, now, did you book around to, oh, just do. So 64.36. And then I've got to add the 67.30 plus 2.94. So 70.24. And we found, now look, this is our 95% confidence interval. Okay? We found our 95% confidence interval. Now, I'm going to pause right there because I've got to talk about what this actually means. Okay? What does this mean? This means, for this example, remember we're talking about like fourth graders and their reading score, right? For this new experimental reading program. We're 95% confident that the actual population mean for reading scores of fourth graders that go through this program is between 64.36 and 70.24. Okay? 64.36. So we're 95%. The actual mean, we don't know what the population mean is, right? But we are 95% confident that it's between these two numbers, okay? We're 95% confident it's between those two numbers. Okay. I'm going to give you an example here, Lori, and I want you to try this one. And if you're, you guys that are watching later, if you want to like pause it and then try it and see if we can get this on our own. So let's say we had, and I'll go over it, of course. Let's say we were looking at, you know, like heights. No, heights is up. It's overdone. What would we take an average of? Let's say we were looking at the average age of incoming freshmen. Let's say the average age of freshmen on our campus, because we have a lot of non-traditional students, right? So let's do the average age of freshmen, and we sampled 50 freshmen. Now, for some reason, we know the standard deviation. To use the process we're doing today, we have to know the population standard deviation. Okay, that's really 8.1. And 8.2, we won't know the population standard deviation. Okay, so we know, it turns out the population standard deviation is like 18. And with this sample, the average we found was 21.4 years old. Okay, 21.4. So I want a 95% confidence interval. Now, what that means is if you have a 95% confidence interval and you know the population mean or population standard deviation, that automatically means that the critical value is 1.96. Okay, we'll go over a 99% here in a minute with the same data, actually. So I want you to find this confidence interval. I got to run and get some water. My throat's starting to hurt. So use those same techniques we just did and find the 95% confidence level. I'll be right back, and then we'll go over it. Okay, I'm going to start down the path. Okay, before we can do anything, we've got to find the standard error. Right? The standard error, which is the population standard deviation over the square root of the sample size. So 18 over the square root of 50. I'm going to do that in the calculator.
0.16.
0.16.
No, wait a minute. I know what I did wrong. Never mind.
Okay. 2.5. Let's do
I'm losing my mind here.
That's okay. Let's do a few decimal places for this. 2.5456. Okay. 2.5456. Now we're going to need that, and we're going to need the critical value to get the margin of error, right? So the margin of error, you just multiply those two together. So 1.96 times 2.5456. And I've got, let's do two decimal places. 4.99 if I rounded it to two decimal places for my margin of error. So that means I've got to add and subtract that to my X bar, right? So it's going to be 21.4 plus or minus 4.99. So minus is going to be 16.41. You can tell this is not real world data, or it wouldn't be that low. I add it, 21.4 plus 4.99. I get 26.39. So now if I ask you to interpret this, you'd say that you're 95% confident the actual average student age on campus is between 16.41 and 26.39 years. Okay? Now, look, this is just me using some real world data. And actually, I'll tell you, I bet the average age on campus is not normally distributed. I mean, the sample would be, but the average one, because there would be a lot of students kind of clumped around 18 and 19, right? But then it would be skewed to the right, because there's a lot of students that come back to campus and go back to school later on. Okay. Now here's the part where you get a little upset with me, because we could do all this in our calculator. But I'll tell you, I can't just do this in the calculator without going over it with you. It wouldn't be fair to you, because later on when we have to really grasp some larger concepts, you have to really kind of know how to do this and understand the margin of error, the critical values, things of that nature. Okay, so let's do one of these in the calculator, and I'm going to do the same exact one. Just pop it in the calculator to show that we should get the same exact answer. Okay, Lori, are you ready?
Uh-huh.
Okay. So you got to remember what buttons to press. You got to go to stat. So the stat button, and then tests. Okay, are you on that test list?
Uh-huh.
If you go down, you'll see Z interval. And the reason it's a Z interval is because we know the population standard deviation. So we're using a Z distribution, okay? Now, it should ask you, you can either put in the data, so that's if we had the sample. If we had like all 50 of these sample points, we could put in the data and just put that in and it would calculate it for us. Now, we know the stats, so we're going to click on stats. And we're going to input what we know. We know that the standard deviation is 18. We know that the X bar, the average age for these students, is 21.4. And we know our N value is 50. Now, it has to be greater than 0 for us. I mean, of course, it's got to be greater than 0. It's got to be greater than 30 for us to use to assume normality, okay? And then it asks for confidence level. So we're going to write this as 0.95 because we're 95% confident. Okay, I believe it's written as a decimal. We'll see here in a minute. Okay, if it's not. And then when we hit calculate, it should give us this interval. Yep. Did you get that?
Yeah. It's mine's weird. Before I could just hit the enter button to continue going down. This time I have to hit the arrow button to go
The
down.
down button. Yeah.
It's like, why are you doing this to me? Yeah, I got 16.411 and 26.389.
Perfect. And we rounded 2 decimal places, so it's a little different. Now, okay, good. This leads us to my next concept, which is, well, what if we wanted 99% confidence? Okay, we know what the 95% confidence interval is. So over here, I'll use another color. We'll use pink just to kind of separate it. And then we'll just use a calculator for this. What if I wanted 99% confidence? And I want you to think for a minute. If I want 99% confidence that I'm actually catching the average population, what I need, will this interval, don't do anything yet, Lori, I want you to think about this. Will this interval be wider or will it be skinnier? If I want 99% confidence that I'm going to catch it.
I'm thinking it would probably be smaller.
I know, that's what everybody thinks. That's why I'm asking. Okay, now hear me out. Hear me out. If you go fishing with a net and you're trying to catch this fish with a net, are you going to be more confident with a smaller net or a bigger net?
A bigger net.
Exactly. That's what this confidence interval means. So if I want 99% confidence that I'm catching this mu right in the river, if I want a higher level of confidence, I need a bigger net. So what happens is this is going to be a wider net. We're going to have because it gives us a better chance, a higher confidence, that we actually catch the mean. Okay? So all I'm going to do, if we go back into this, so remember it was stat, tests, and then we go down to Z interval again. Now your info should be still in there, I think. Right?
Yeah.
All we're going to change is that confidence level. So instead of 0.95, we're going to be 0.99. Now, that 99% confidence means where our alpha is 0.01. That's going to pop up later on. So remember, 95% meant 0.05 alpha. 99% means 0.01 alpha. So we're going to calculate that.
I got 14.843 and 27.957.
Perfect.
So one goes down and one goes up.
Which means we have got a wider net, right?
Yeah.
Yeah. Now we've got a wider net. And if we want to know the margin of error for this one, let's say we just wanted to know it from calculating it. Remember, the average is the same, 21.4. So you could take like 27.96 there, 27.96, and subtract the average, and that'll give you the margin of error. So this margin of error is 6.56. Where remember our 95% margin of error was 4.99. So we've got a 1.5 year larger margin of error. Look, so this would mean I'm 99% confident that my margin or that my average freshman age on campus is between 14.84 and 27.96. Okay, it's somewhere in between there. And we're 99% confident it's somewhere in between that. Have you been following? If the polling stuff interests you with this last election or with any election, if you go on,
we've been following it. When I have a husband who is nothing but news and politics.
Well, if you
couldn't even, let's put it this way, I couldn't even do my homework last night because I was busy doing it, and he was talking to me saying, "Here, look at this map. Look at this map. The red here, it's all red. Why is he?"
Yeah, and I'm not going to get into the red and blue stuff, but if you look at any good polling website, will give you a margin of error. And then they're going to tell you, oh, well, we were within our margin of error. And a very famous one is 538, or a popular one, I should say, is 538. And they were barely within their margin of error on the popular vote, this past one. So it kind of shows you how, look, I don't remember, I think their margin of error was 80%. If you look at their website, it'll tell you. It's kind of neat. You go to their website and look at their statistics or their predictions. They do an 80% margin of error, which means they're 80% confident. They make all those beforehand, right? They're 80% confident that the actual population. I think they do theirs on the percent that each candidate gets. So they're 80% confident that, let's say Joe Biden will get between two numbers, and they use an 80%. 80% is just a good real world number to use. In the like kind of not theoretical world, that's not really a good way to say it, but in like the academia, you would usually use 95% or 90 or 99. Those are the three most common in academia. But then in the real world, it's 80 is not a bad one. I mean, that means you're only going to be wrong 20% of the time, right? That's not too bad. They were almost wrong. he was. Nate Silver is the guy that runs that one. He was almost wrong. Again, by the way. But that's another discussion for another day.
Yeah.
But it is interesting. So when you're watching this does relate to some real world stuff. It would have been fun to get to this stuff right before the election, because you can kind of see how it's used in the real world.
Yeah.
Your book. So I'm kind of following along, making sure I don't forget anything. On page 360, your book does go over the confidence interval and what it means. We've gone over that already, and the confidence level, and then it goes over constructing the intervals of different levels, which is fine. There's nothing wrong with that. We've gone over that with the calculator, and I've kind of shown you that with the calculator. Yep, that's not a big deal. We have done that now. And that, yes. Yeah, okay. I'm gonna bring the book over because this is hard to recreate just in my. Your book does a really good example or an explanation of confidence levels here. Okay, so notice like over here, I bet this is 90% confidence. Does it say that? We're gonna assume it. Oh wait, the diagram on the left represents 70% confidence intervals. 8.8. Left is 70% confidence levels for a population mean, and then 95% and then 97. So look, notice this is 70% confidence levels. Let's see if I can change the focus here and get a little better. What this means is if we did these are all surveys, right? These are all samples, okay? Each little line here represents a sample, okay? And every time we take a sample, we're going to get a different X bar, right? But in that last example I did, we sampled 50 freshmen, right? I'm going to go out and I scoop up 50 different freshmen and I take a sample. It's going to be a different average age, right? That's what's going to happen. Right. That's part of the difference between algebra and statistics. In algebra, it's very black and white. In stats, we're going to get gray areas, right? So what this means is, look, the actual mean is out there somewhere. That's the population mean down there, right? We don't know what it is. But when we attach the margin of error, that's our net. We're casting our net, right? And we're saying for this example, they did 70% confidence. So each one of these has a 70% confidence of actually catching that mu. And notice, some of them didn't catch it. Hold on, let me see if I've got like a in here. Yeah. Look, that example right there. And let's just say it was for heights again. I don't know what this was, but let's say it was, or not heights, but let's say it was that ages. We did a sample of 50. We attached our margin of error on both sides. We just didn't catch the mu. Now we'll never know that, right? Mm-hmm. We'll never know that because we don't know what the actual mean is. I mean, for ages on campus, we could find the mean. But if it's something that we just didn't know, we would never be able to find it. We would not know that we actually didn't catch it. Okay. Now, like this one though, got really close, and when we attached the averages on left or the margin of error on left and right, it caught it. Okay. And notice now, so that's 70%. That's 70%. So then we've got 95% here. Notice it's a wider gap, right? We've got larger margins of error. There's only a few here that don't catch it. I see this guy doesn't catch it. That one doesn't catch it. Oh, this guy right here got too low, right? But there's only a few that don't catch it because we're 95% confident. We're going to assume 5% of the time our net doesn't catch the actual population mean. Okay, we have to assume it 5% of the time, and we're with whatever we're doing kind of determines our interval. Like if I'm trying to get the average height on campus, I'm not worried 70%, 80%, whatever. But if I am trying to get the average, let's say it's something medicinal, if it's something with like a vaccine, I need a higher level of confidence that I'm actually catching that it'll work, right? So I need a higher level of confidence. Maybe this is 99? Oh, 99.7%. And notice how wide the intervals are. Every single one of them catches it because, like this guy over here, right? See that? So it's the same one over here, but now it's so big it actually caught it at the very edges. This is actually what happened if you go to 538. The average was way higher or lower, I think, actually, for one of the candidates, and it caught it, and it barely caught the actual. Because what's nice about polling is people have to go freaking vote, and when in the end you know a number, right? So you know what the population sample is, which is kind of neat about polling too. So you wind up knowing the population sample, where a lot of times we'll never know this population mean, right? I mean, we're never going to know the average height of fourth graders. Period. Right? That's not going to happen. Okay. That's my rant on that. So, higher level of confidence, higher margin of error gives us the wider net. I'm going to ask you to explain that on the test. And I know, and it's okay. You don't have to use perfect words, but I really want you to interpret, hey, if we have a larger confidence level, that means we have to have a larger margin of error, right? Which means we have a higher probability of catching the population mean. We have a higher probability of catching population mean. Oh, go back there. I don't like this. It's been me versus this desktop thing. It's been fun plot twist and not plot twist, fun theme of 2020. Your book then goes over the necessary sample size. I wanted to talk about that just for a minute. It's not necessarily that important, but it's not important. So your book says, we have seen that we can make the margin of error smaller if we are willing to reduce our level of confidence, right? That makes sense. Kind of the vice versa statement. If we want a smaller margin of error, we just have to reduce our level of confidence. We can also reduce the margin of error by increasing the sample size, right? If we increase the sample size, we can become more confident without really increasing the margin of error. Okay.
What page are we on?
I'm sorry, page 368. It's at the bottom.
Oh, okay.
Yeah.
I'm trying to find where we're at.
Yeah, it says we can also reduce the margin of error by increasing the sample size. We can see this by looking at the formula for margin of error. Now, look, I forgot to talk about this, but I'm going to right now. So margin of error equals Z alpha over 2. This is our, oh my gosh, what's the word that I used? My brain just let it go. Oh my gosh. I want to make sure I get this word right. Critical value. That's the critical value, okay? And remember I talked about the alpha over 2? That's the area to the left of our sample. So alpha over 2. You don't have to worry too much about that, but just know it's our critical value. And remember, to find margin of error, you multiply the critical value by the standard error. So times sigma over the square root of n. Now, sometimes we want to have a certain margin of error. In your book, we'll do this with an example, and I'm going to show you how to work this one with an example. Your book solved it out, like solve for n, but I'm going to show you a little different way to do it. It's a little easier to do with numbers. So let's look at their example on 8.7. It says scientists want to estimate the mean weight of mice after they have been fed a special diet. From previous studies, it is known that the weight is normally distributed with a standard deviation of 3 grams. How many mice must be weighed? So we want to know n. So that a 95% confidence interval, that is 95% confidence interval, remember that z is 1.96. We'll have a margin of error of 0.5. Okay. I'm going to plug this in and then solve for n. So our margin of error is 0.5. Our z value is 1.96 times our sigma is 3, and we want to know what n is. So we're going to dig this out. Okay, and it's a little easier if we just solve it with the numbers instead of going through and solving it the other way. So if I multiply a number times a fraction, you just multiply the numerator and the number. So this winds up being 0.5 equals 1.96 times 3. So 2.88 over the square root of n. Okay, now to get the square root of n to the other side, you multiply it to that side. So you wind up with 0.5 times the square root of n equals 2.88. Right? It's in the denominator. You multiply it to the other side. Then I want the 0.5 to go away, so I'm going to divide 0.5 on both sides. So I get the square root of n equals 2.88 divided by 0.5. So 5.76. You know what? I didn't multiply something correct. No, I didn't. 1.96 times 3. 1.96 times 3 is not 2.88. It's 5.88. That's my brain. I don't know what I was doing. So I'm going to correct this real quickly.
I'll tell you why, because I did the same thing. I hit the 1, but it didn't go on there.
Yeah, that's exactly
1.96.
right.
It was just 0.96.
Yeah. So 5.88 divided by 0.5 is 11.76. Okay, so I'm going to rewrite this one. 11.76. Now we've got to square both sides to get the radical to go away. And you wind up with 138.2972. Now look, even though this, in math we would round this down, if we want this confidence level, we've got to round it up to 139. Because we need that extra person to get there. Okay? So that's just algebra. And you're always going to round up. Okay, you're always going to round up.
Equals 11.76 square and square 76 square 3
Okay? You'll see this in the homework, and I want you to try in the homework, and if it's still not clicking, then ask me, and I don't mind going back over it. It's not a big deal, but it is based off that equation.
Yeah, on your n right above the n139, shouldn't it be 2976, even though you're rounding it off?
Yeah, you're right, 2976. Yeah. it goes up no matter what. That in rounds up because you need the whole person, right? If we do
Right.
138, we won't get there, so we've got to do 139. Okay, so for homework in this section, this is 8.1. For homework, I want you to start in the chapter. Number 1 starts on 376. Actually, man, I'm not even worried about that because the that goes over the inverse norm. Yeah, so a bunch of this homework is really based on doing this by hand, okay? And we did it in the calculator. So I'm actually going to get real picky and choosy on this one. I want you to do number 3. You need to do that one by hand, where it gives you the standard error and it gives you the confidence level, and you've got to find the margin of error. Number 4.
Okay, that's page 362.
Yep.
So number 3.
Number 4. I want you to do. Yeah, number 4, 5, 6. I don't know why I'm not. Okay, hold on. 3 through. 3 through 8. Then 9, it's one to use a mini tab. We're not using mini tab. 11 through
You didn't want to do 9 and 10 on 365?
No, because it's talking about using mini tab, and we're using a calculator. Yeah, I have a feeling if you do this homework, you're gonna have a lot of questions when we get back, which is great. Let's do 11 through 67, and on these, if you want to do odd, that's fine. But I want you to hit 3 through 8 first, and then 11 through 67 odd. It starts on page like 370.
368 is 11 and 12.
368, and then it goes forward from there. But I'll tell you, this should bring up a lot of questions.
Yeah, then 13 and 14 is on page 369.
Yeah. So I expect a lot of questions, Lori, when we get back.